Hello and welcome to Late Physics. If you enjoy calm explorations of the universe and the strange ideas that shape modern science, take a moment to like the video and subscribe to the channel. It really helps the channel grow and lets more curious minds find these long-form journeys through physics. And before we begin, I'd love to know where in the world you're watching or listening from tonight. Maybe you're relaxing at home, winding down after a long day, or perhaps you're somewhere quiet under the night sky. Wherever you are, feel free to leave a comment and let us know. Because tonight's topic connects directly to something remarkable about that place you're sitting right now. The chair you're in, the floor beneath your feet, the air in the room around you. According to modern physics, none of these things are really solid objects at all. Instead, everything around you, including you, may actually be ripples in invisible fields that stretch across the entire universe. Fields that pass through your walls, fields that extend through the Earth, fields that fill the emptiness between galaxies. In fact, if physicists are right, the entire universe is less like a collection of things, and more like a vast ocean of interacting fields gently vibrating in countless patterns. Some of those vibrations appear to us as electrons, some appear as light, some form the atoms that build planets, stars and living creatures. Even empty space, what we normally think of as nothing, turns out to be quietly alive with activity. Invisible fields are constantly fluctuating. Particles briefly appear and disappear. Energy flickers in and out of existence. All of it happening silently beneath the surface of reality. And yet this idea, that everything is made of fields, did not arrive all at once. It emerged slowly, across more than a century of discovery, through the work of physicists trying to understand electricity, light, atoms, and the strange behavior of quantum particles. Along the way, something surprising happened. The deeper scientists looked into matter, the less solid it seemed to become. Atoms dissolved into smaller particles. Particles began behaving like waves, and eventually even those particles seemed to vanish entirely, replaced by something far stranger. Fields. Fields that fill the entire universe. Fields that cannot be switched off. Fields that are always present, everywhere. What we call a particle may simply be a tiny vibration travelling through one of these fields, like a ripple moving across the surface of water. If that idea sounds abstract, you're not alone. Even the physicists who first discovered it struggled to believe it. But experiment after experiment has confirmed the same picture. The universe appears to be built not from objects, but from patterns within something deeper. Tonight, we're going to slowly explore that idea together. We'll start with the moment when physics first began to suspect that matter might not be solid at all. Then we'll follow the discoveries that led scientists toward quantum field theory, one of the most successful scientific frameworks ever created. Along the way, we'll encounter strange concepts like the quantum vacuum, where even empty space is alive with invisible fluctuations. We'll look at the Higgs field, which quietly gives mass to everything around us. We'll explore mysterious fields that might make up dark matter, and theories suggesting that space-time itself may emerge from even deeper structures. And by the end, we may find ourselves looking at the universe in a completely different way. Not as a place filled with objects, but as a cosmic symphony of fields, vibrating quietly across space and time. So settle in, get comfortable, and let your mind wander a little. Because the story of the quantum fields behind everything begins with a surprising realization. Matter, it turns out, was never really solid to begin with. Take a moment to look around wherever you are right now. Perhaps there is a table nearby, a wall, a lamp, maybe a phone in your hand. Every one of these things feels solid and familiar. They seem like collections of objects made from matter, sitting quietly in space. For most of human history, that is exactly how people imagine the universe. Reality was thought to be built from tiny pieces of stuff. Ancient philosophers like Democritus imagined the world as made from indivisible particles called atoms. Centuries later, early modern science inherited a similar picture. Matter was made of small objects, and those objects moved around inside empty space. But modern physics tells a very different story. Over the past century, scientists have gradually come to suspect that the universe is not really made of particles at all. Instead, it appears to be built from something far more subtle and far more strange. Fields. A field is something that exists everywhere in space. It is not an object and it does not sit in one place. Instead, a field assigns a value to every point in the universe. To understand the idea more intuitively, imagine standing on a hillside on a calm day. At every point on the hill there is a specific height above sea level. If you walked across the landscape, that height would change smoothly beneath your feet. A gravitational field works in a similar way. At every location around Earth, gravity has a certain strength and direction. Fields describe how forces exist across space. Today, physicists believe the universe is filled with many different kinds of fields. Some carry forces, some create matter, and some quietly permeate every corner of existence, whether anything seems to be there or not. The strange part is this. What we normally call particles may simply be tiny vibrations inside these fields. Imagine a perfectly calm lake stretching out in every direction. The surface of the water is smooth and still. Now imagine tossing a small stone into that lake. A ripple spreads outward from the point of impact. That ripple is not a separate object from the water. It is simply a moving disturbance within the water itself. According to modern physics, something very similar may be happening all around us. An electron is not necessarily a tiny solid sphere moving through space. Instead, it may be a small ripple in something called the electron field. That field fills the entire universe. When it vibrates in a particular way, the vibration appears to us as an electron. In the same way, photons, the particles of light, are excitations of the electromagnetic field. Quarks are excitations of quark fields. Even the forces that hold atoms together arise from their own fields. In this picture, particles are no longer the fundamental building blocks of reality. Fields are. This idea did not appear suddenly. It emerged gradually as scientists struggled to understand electricity, magnetism, and light during the 19th century. One of the most important figures in that story was a Scottish physicist named James Clerk Maxwell. Before Maxwell, electricity and magnetism were known as two separate phenomena. Static electricity could make hair stand on end. Magnets could pull iron nails across a table. Scientists had measured these effects, but the deeper connection between them was unclear. Maxwell brought these ideas together in the 1860s through a set of equations that described how electric and magnetic fields interact. When written in mathematical form, these equations describe how changing electric fields create magnetic fields, and how changing magnetic fields create electric fields. In simple spoken form, the relationship can be summarized like this. Electric fields that change over time create magnetic fields, and magnetic fields that change over time create electric fields. Together, they form a single entity called the electromagnetic field. When Maxwell examined the behavior of this field, he noticed something remarkable. His equations predicted waves moving through space at a very specific speed. That speed turned out to match the measured speed of light. The conclusion was astonishing. Light itself is an electromagnetic wave. What we experience as visible light is simply a ripple traveling through the electromagnetic field. This was one of the first hints that reality might be structured around fields rather than objects. Once scientists began thinking in terms of fields, the concept spread into other areas of physics. Gravitational effects could be described as gravitational fields. Magnetic behavior came from magnetic fields. Later discoveries suggested that atoms and subatomic particles might also arise from fields. The idea quietly grew stronger throughout the 20th century. As experimental techniques improved, physicists discovered that atoms were not solid spheres. They were mostly empty space. Inside them were smaller particles such as electrons, protons, and neutrons. Later still, those particles were found to contain even smaller components called quarks. At each step, matter seemed to dissolve into something more abstract. Particles behaved like waves. Waves sometimes behaved like particles. And the mathematics describing their behavior increasingly pointed toward an underlying field structure. Eventually, this perspective became the foundation of modern particle physics, through a framework known as quantum field theory. Quantum field theory proposes that every type of particle corresponds to its own field, spread throughout the entire universe. Electrons arise from the electron field. Photons arise from the electromagnetic field. Quarks come from quark fields. In this sense, what we normally think of as empty space is actually full of invisible structure. Even the vacuum, the emptiest environment we can create in a laboratory, still contains these fields. They cannot be turned off. They exist everywhere, all the time. This idea can feel almost philosophical. The table beside you may appear solid and permanent, but at the deepest level it may be better understood as a stable pattern within several interacting quantum fields. Those fields are vibrating in extremely precise ways, producing the atoms and molecules that form the material world. A helpful comparison comes from music. Imagine a violin string stretched tightly between 2 points. When the string is still, it is quiet and invisible in the background. But when it vibrates, it produces sound. The note you hear depends on the way the string moves. In a similar way, fields can vibrate in different patterns. Each pattern corresponds to a different particle. In this sense, the universe may be less like a collection of tiny objects and more like an enormous instrument whose strings extend across the whole of space. Scientists around the world are working to understand these fields in greater detail. At the European Organisation for Nuclear Research, better known as CERN near Geneva, researchers operate the Large Hadron Collider. This enormous circular accelerator sends beams of particles racing around a tunnel 27 kilometers in circumference before smashing them together at enormous energies. By studying the debris from those collisions, physicists can observe how fundamental fields behave when they are pushed to extreme conditions. Similar work is carried out at other laboratories as well. The Deutsches Elektronensynchrotron, usually called DESY, in Hamburg studies particle interactions and the structure of matter. The ESLAC National Accelerator Laboratory in California explores particle physics, astrophysics, and powerful X-ray imaging techniques. These facilities allow scientists to probe the behavior of fields that normally remain hidden beneath everyday reality. When particles collide at high energy, the fields that created them can briefly produce new vibrations, new particles, and entirely new phenomena. Each experiment helps physicists test the idea that fields truly are the underlying fabric of the universe. If this picture is correct, then what we experience as matter, energy, and even the forces of nature are simply patterns emerging from deeper structures. Objects become events, particles become vibrations, and the universe itself becomes something closer to a vast ocean of fields, quietly fluctuating everywhere at once. It is a perspective that changes the way we think about the nature of reality, not as a collection of separate things scattered through empty space, but as a continuous physical system where everything is connected through fields that stretch across the entire cosmos. And once you begin looking at the world through that lens, even the most familiar objects start to feel a little different. Because beneath the surface of everything we touch and see, invisible fields are always there, gently vibrating, quietly shaping the structure of the universe. For most of history, matter seemed reassuringly solid. A stone felt hard in your hand. A table resisted when you leaned against it. A metal tool could hammer a nail into wood. Everything about daily experience suggested that the universe was built from sturdy pieces of material. Even early scientific theories carried this intuition forward. In the 17th century, Isaac Newton described the motion of objects as if the universe were a vast stage filled with tiny particles moving through empty space. Those particles pushed, pulled, and collided with one another, producing the complex world we see around us. This view worked remarkably well for describing many everyday phenomena. It explained how planets orbit the sun, how cannonballs travel through the air, and how pendulums swing back and forth. But as the 19th century gave way to the 20th, careful experiments began revealing that matter was far stranger than anyone had imagined. The first cracks in the classical picture appeared when scientists began investigating the structure of atoms. For centuries, atoms had been treated mostly as a convenient idea. Chemists knew that substances combined in fixed ratios, and atoms provided a helpful way to think about those patterns, but no one had directly observed what an atom looked like internally. That began to change in the late 1800s, when researchers started experimenting with electrical discharges inside glass tubes filled with gas. One of the scientists leading this work was a physicist named Joseph John Thomson at the Cavendish Laboratory in Cambridge. Thomson studied mysterious streams of particles called cathode rays, which appeared when electricity passed through evacuated tubes. In 1897, after careful measurements of how these rays responded to electric and magnetic fields, Thomson reached a remarkable conclusion. The rays were made of tiny, negatively charged particles much smaller than atoms. He had discovered the electron. This was an extraordinary moment in the history of science. Atoms, once thought to be indivisible, now appeared to contain smaller components. Matter was not built from solid building blocks after all. Even the atom had an internal structure. Thomson proposed a model of the atom sometimes described as the plum pudding model. In this picture, the atom was imagined as a soft sphere of positive charge with negatively charged electrons embedded within it, somewhat like raisins in a pudding. It was a creative attempt to explain the new evidence, but it would not last long. A few years later, another physicist would perform an experiment that reshaped our understanding of matter even more dramatically. Ernest Rutherford, working at the University of Manchester in the early 1900s, designed a clever test involving extremely thin sheets of gold foil. He and his collaborators, including Hans Geiger and Ernest Marsden, fired tiny positively charged particles called alpha particles toward the foil and observed how they scattered. According to Thomson's model, the alpha particles should have passed through the atom with only small deflections. The positive charge in the plum pudding model was spread out smoothly, so there was nothing inside the atom strong enough to cause a large change in direction. But that is not what Rutherford's experiment revealed. Most of the alpha particles passed straight through the gold foil without any noticeable deflection at all. However, a small number bounced off at very sharp angles. A few even came almost straight back toward the source. Rutherford later described this result with quiet amazement. It was, in his words, almost as incredible as if someone fired a 15-inch artillery shell at a piece of tissue paper and it bounced back. The only explanation was that most of the atom must be empty space. The positive charge and most of the mass had to be concentrated in a tiny central region that Rutherford called the nucleus. The electrons must orbit far away from this dense center. This discovery changed the image of the atom almost overnight. Instead of a soft sphere filled with charge, the atom now resembled a miniature planetary system. A small nucleus sat at the center, while electrons moved around it in surrounding space. But even this picture, though revolutionary, turned out to be incomplete. If electrons were simply orbiting the nucleus like planets orbit the Sun, classical physics predicted that they should gradually lose energy by emitting electromagnetic radiation. As they lost energy, their orbits would shrink until they spiraled into the nucleus. If that happened, atoms would collapse in a tiny fraction of a second. Matter itself would not be stable. Clearly something else was happening. The next major step came from a Danish physicist named Niels Bohr. In 1913, Bohr proposed a new model that combined Rutherford's nuclear atom with the emerging ideas of quantum theory. Bohr suggested that electrons could occupy only certain specific orbits around the nucleus. These allowed orbits corresponded to fixed energy levels. As long as an electron remained in one of these special states, it would not lose energy. An electron could jump between these levels by absorbing or emitting a packet of light called a quantum. This idea explained the precise spectral lines observed in experiments with hydrogen gas. Bohr's model was remarkably successful in explaining atomic spectra, but it still treated electrons as tiny particles traveling along well-defined circular paths. Soon, even this picture would begin to change. One of the scientists who expanded Bohr's work was the German physicist Arnold Sommerfeld. Working in Munich during the 1910s and 1920s, Sommerfeld refined the atomic model by introducing elliptical orbits and subtle corrections based on Albert Einstein's theory of special relativity. Sommerfeld also introduced additional quantum numbers that helped describe the structure of atomic energy levels more precisely. His refinements allowed the model to explain fine details in atomic spectra that Bohr's original theory could not fully account for. Yet despite these improvements, physicists were beginning to suspect that the entire idea of electrons moving along precise orbital paths might be misleading. As experiments grew more precise, electrons increasingly behaved less like miniature planets and more like something far stranger. The old mechanical picture of the atom was slowly dissolving. Electrons sometimes behaved like particles. In other experiments they behaved like waves. Their position could not be predicted exactly, only described through probabilities. This shift in understanding transformed the atom from a simple mechanical system into a dynamic quantum system, governed by deeper principles. Instead of imagining electrons circling the nucleus along tidy tracks, physicists began describing them as clouds of probability. These clouds represented regions where the electron was likely to be found. The atom was no longer a tiny solar system. It was a constantly shifting pattern of energy and probability, and once matter had reached this stage of abstraction, the transition to field-based thinking became much easier. If electrons were not truly solid objects, then what exactly were they? Why did they behave like waves in some experiments and particles in others? These questions open the door to a new perspective. Perhaps electrons were not objects moving through space at all. Perhaps they were manifestations of something deeper. Perhaps they were disturbances within fields that filled the universe. By the early decades of the 20th century, the classical image of matter as solid building blocks had almost completely dissolved. In its place stood a far more subtle picture of reality. Atoms were mostly empty space, electrons behaved like waves of probability, and the search had begun for a deeper framework capable of explaining what matter really was. The answer, it seemed, would lead physicists toward the strange and beautiful idea that the universe might be built not from particles, but from fields that exist everywhere. At the beginning of the 20th century, physics found itself in an unusual situation. Many scientists believed that most of the major mysteries of nature had already been solved. The laws of motion described by Isaac Newton worked beautifully for planets, falling apples, and cannonballs. James Clerk Maxwell's equations explained electricity, magnetism, and light with remarkable precision. The universe appeared orderly and understandable, and yet a few stubborn problems refused to cooperate with the existing theories. Small inconsistencies began appearing in experiments involving heat, radiation, and the behavior of atoms. At first, these puzzles seemed minor, but they slowly opened the door to one of the most profound revolutions in scientific history. The story begins in Berlin in the year 1900, when a German physicist named Max Planck was studying a problem known as blackbody radiation. A blackbody is an idealized object that absorbs all incoming light and then re-emits energy depending on its temperature. Physicists had been trying to calculate the exact pattern of radiation produced by heated objects such as glowing metal or the surface of a star. Classical physics made a prediction that turned out to be catastrophically wrong. According to the existing equations, the energy emitted at short wavelengths should increase without limit. In other words, hot objects should produce an infinite amount of ultraviolet radiation. This absurd prediction became known as the ultraviolet catastrophe. Planck approached the problem from a new angle. In order to make the mathematics match experimental observations, he proposed a radical idea. He suggested that energy is not emitted continuously. Instead, it is released in tiny discrete packets. These packets of energy became known as quanta. Planck discovered that the energy carried by each packet depended on the frequency of the radiation. In spoken form, the relationship can be expressed clearly. Energy equals Planck's constant multiplied by frequency. Planck himself initially treated this idea as a mathematical trick. He did not immediately believe that energy was truly quantized in nature, but a few years later, another physicist would take the idea far more seriously. In 1905, a young Albert Einstein published a paper explaining the photoelectric effect. This phenomenon occurs when light shines on certain metals and ejects electrons from their surfaces. Experiments showed that the energy of the ejected electrons depended on the frequency of the light, not simply its intensity. Classical wave theory could not explain this behavior. Einstein proposed that light itself must come in discrete packets of energy. These packets later became known as photons. With this idea, light displayed a strange dual personality. In some experiments, it behaved like a wave spreading through space. In others, it behaved like a collection of particles delivering concentrated bursts of energy. This strange dual nature became known as wave-particle duality. It was the first hint that the microscopic world does not obey the same intuitive rules as everyday objects. Soon the mystery deepened. In the 1920s, physicists began studying the behavior of electrons moving through crystals and narrow openings. When electrons passed through two closely spaced slits and struck a detection screen, they produced an interference pattern. This pattern looked exactly like the wave interference seen with ripples on water, but electrons were supposed to be particles. The experiment suggested something extraordinary. Individual electrons behaved as if they were spreading out like waves and interfering with themselves. Even more remarkably, the pattern emerged gradually as individual electrons arrived one by one at the screen. Each electron behaved like a tiny particle when detected, but the overall pattern revealed wave-like behavior. The quantum world seemed to be blurring the distinction between particles and waves. To make sense of this strange behavior, several new mathematical frameworks emerged almost simultaneously. One of them came from the Austrian physicist Erwin Schrödinger. In 1926, Schrödinger developed a wave equation describing how the quantum state of a particle evolves over time. This equation treated particles such as electrons not as tiny solid objects, but as wave-like entities described by a mathematical function. That function became known as the wave function. In words, Schrödinger's equation describes how the wave function changes over time based on the energy and environment of the system. Although the mathematical form of the equation is complex, its conceptual meaning is surprisingly elegant. It provides a rule that predicts how probability waves evolve in the quantum world. But what exactly did the wave function represent? That question was answered by another physicist working closely with Schrödinger. Max Born, a German physicist and mentor to many future Nobel Prize winners, proposed a striking interpretation. Born suggested that the wave function does not represent a physical wave of matter. Instead, it represents a wave of probability. The square of the wave function gives the probability of finding the particle at a particular location. In spoken form, the principle can be summarized clearly. The probability of finding a particle equals the square of the wave function. This interpretation transformed quantum mechanics from a deterministic theory into a probabilistic one. Instead of predicting exact trajectories for particles, quantum mechanics predicts the likelihood of different outcomes. Particles became clouds of possibility, rather than precisely defined objects. At the same time, another powerful approach to quantum mechanics was being developed in Germany by Werner Heisenberg. Heisenberg introduced matrix mechanics, a mathematical framework that focused entirely on observable quantities such as energy levels and transition frequencies. From this work emerged one of the most famous principles in physics, the Heisenberg uncertainty principle. In simple terms, this principle states that certain pairs of physical properties cannot both be known with unlimited precision. The most well-known example involves position and momentum. The relationship can be expressed in spoken form as follows. The uncertainty in position multiplied by the uncertainty in momentum can never be smaller than Planck's constant divided by 4 times pi. This principle is not a limitation of measurement technology. It reflects a fundamental property of nature. Particles do not possess perfectly defined positions and momenta simultaneously. Instead, they exist within ranges of possible values described by probability. During this period, another important figure quietly contributed to the development of quantum theory. Pascal Jordan, a German physicist working with Max Born and Werner Heisenberg, helped develop the mathematical structure that would later evolve into quantum field theory. Jordan explored how quantum systems could be described using operators and commutation relationships. His work also introduced the idea that fields themselves might be quantized, much like particles. Although Jordan's contributions are sometimes overshadowed by more famous names, his work helped bridge the gap between early quantum mechanics and the later development of quantum field theory. By the late 1920s, the picture of the microscopic world had changed dramatically. Electrons were no longer simple particles orbiting the nucleus. They behaved like probability waves. Light behaved both as a wave and as particles called photons. The uncertainty principle placed fundamental limits on what could be known about physical systems, and the mathematics describing these phenomena increasingly suggested that particles might not be fundamental objects at all. Instead, they looked more like excitations within deeper mathematical structures. It was as if the solid building blocks of matter were dissolving into patterns of energy and probability. Once this idea took hold, a natural question emerged. If particles are waves, what exactly is waving? What is the underlying medium that supports these strange probability waves? Answering that question would eventually lead physicists toward a powerful new framework, one that suggested the universe might be built not from particles at all, but from fields that extend across the entire cosmos. By the late 1920s, physicists had reached a strange and fascinating crossroads. Quantum mechanics had revealed that particles behaved like waves. Albert Einstein's theory of special relativity had already shown that space and time were deeply intertwined, forming a single structure called space-time. Each of these theories worked extremely well within its own domain. But there was a problem. Quantum mechanics had been developed largely without considering the effects of relativity. Meanwhile, relativity described the behavior of objects moving close to the speed of light, but did not incorporate the strange probabilistic rules of the quantum world. To truly understand the smallest building blocks of nature, these two frameworks needed to be combined. One of the physicists who took on this challenge was a quiet and mathematically gifted scientist named Paul Dirac. Dirac worked at the University of Cambridge, and in the year 1928, he introduced an equation that would become one of the most remarkable discoveries in the history of theoretical physics. Dirac's goal was straightforward in principle, but extremely difficult in practice. He wanted an equation that described the behavior of electrons while respecting both the rules of quantum mechanics and the requirements of special relativity. The equation he eventually produced did exactly that. When written mathematically, it was compact and elegant, but its consequences were astonishing. Dirac's equation predicted that the electron possessed an intrinsic form of angular momentum called spin. This property had already been suggested by experimental results, but Dirac's equation showed that spin emerged naturally from the mathematics itself. Even more surprising, the equation contained additional solutions that seemed to describe particles with the same mass as the electron, but with the opposite electric charge. At first, this result puzzled Dirac. Negative energy solutions appeared in the mathematics, and they did not seem to correspond to any known physical objects. Dirac proposed a bold interpretation. He suggested that these solutions represented a new kind of particle. It would behave exactly like an electron but carry a positive electric charge. In other words, the universe should contain a positively charged counterpart to the electron. Today we call this particle the positron. At the time, the idea sounded almost absurd. No one had ever observed such a particle. But in 1932, an American physicist named Carl Anderson was studying cosmic rays at the California Institute of Technology. Using a cloud chamber placed inside a magnetic field, Anderson observed a particle leaving a curved track that matched exactly the predicted properties of Dirac's positron. Antimatter had been discovered. The existence of the positron revealed something profound about the nature of the universe. For every particle of matter, there could exist a corresponding antiparticle with opposite electric charge. Electrons have positrons, protons have antiprotons, even neutrons have antineutrons. When a particle meets its antiparticle, the two can annihilate each other and release their mass as energy. This process is not just theoretical. It happens regularly in particle accelerators and in certain natural radioactive processes. The energy released in such annihilations follows Einstein's famous relationship: energy equals mass multiplied by the speed of light squared. This prediction of antimatter was the first major hint that quantum theory was revealing deeper structures beneath the familiar particles of matter. Dirac's equation also raised another intriguing idea. If particles and antiparticles could appear from the mathematics of the theory, perhaps empty space itself was not truly empty. Dirac imagined the vacuum as a vast sea filled with negative energy states, sometimes described as the Dirac sea. In this picture, the vacuum contained an enormous number of invisible states that could give rise to particles under the right conditions. Although the details of this interpretation were later replaced by more refined theories, the core insight remained important. The vacuum was not simply empty space, it possessed a complex structure that could produce particles. At the same time, other physicists were uncovering deeper principles hidden within the mathematics of quantum theory. One of them was Wolfgang Pauli, an Austrian physicist known both for his sharp intellect and his famously blunt criticism of sloppy reasoning. Pauli introduced a powerful rule known as the Pauli exclusion principle. This principle states that no two identical fermions, such as electrons, can occupy the same quantum state at the same time. The Pauli exclusion principle explains the structure of the periodic table and the stability of atoms. Electrons fill atomic orbitals in layers, and this arrangement determines the chemical behavior of elements. Without the exclusion principle, matter would collapse into extremely dense states, and the familiar structure of chemistry would not exist. Pauli also played a crucial role in developing the theory of spin and in clarifying the mathematical framework of quantum mechanics. Another important figure was Eugene Wigner, a Hungarian physicist who explored the deep connection between physics and symmetry. Wigner showed that many of the laws of physics can be understood through mathematical symmetry transformations. For example, if the laws of physics remain unchanged when a system is rotated, that rotational symmetry corresponds to the conservation of angular momentum. Symmetry principles turned out to be far more than mathematical curiosities. They became guiding rules for constructing physical theories. These developments were gradually pointing physicists toward a surprising conclusion. The mathematics describing particles was beginning to resemble the mathematics describing fields. In classical physics, fields such as the electromagnetic field were already familiar. They filled space and could oscillate in the form of waves such as light. Quantum mechanics now suggested that particles themselves might behave like quantized excitations of similar fields. Imagine a stretched surface of water again. When the surface is calm, the lake appears perfectly still. But if a small disturbance occurs, ripples move outward. Those ripples are not separate objects, they are temporary patterns in the water itself. A similar idea began to emerge in quantum theory. Perhaps electrons were not fundamental particles in the traditional sense. Instead, they might be tiny disturbances in a deeper electron field. Photons would then be disturbances in the electromagnetic field. Other particles would correspond to their own underlying fields. This idea gradually evolved into a new theoretical framework called quantum field theory. In quantum field theory, the fundamental ingredients of reality are fields that exist everywhere in space and time. These fields are quantized, meaning their excitations appear as discrete particles. When a field vibrates in a specific way, we observe a particle. When the vibration disappears, the particle vanishes as well. This perspective transformed the meaning of the word particle. Particles were no longer the basic building blocks of nature. Instead, they became localized events within fields that fill the entire universe. The implications of this shift were profound. Matter, energy, and even empty space all began to look like different expressions of the same underlying framework. Fields became the true foundation of reality, and what we perceive as particles were simply the visible ripples on a much deeper and more continuous structure that stretches across the cosmos. As the 20th century moved forward, physicists were beginning to see the outline of a new framework for understanding the universe. Quantum mechanics had revealed that particles behave like waves of probability. Albert Einstein's theory of special relativity had demonstrated that space and time form a single interconnected structure called space-time, and that the speed of light sets a fundamental limit on how information and energy can travel. Each of these theories worked beautifully on its own. But nature does not separate itself into tidy categories. The world of atoms and particles exists inside space-time, and particles often move at speeds close to that of light. To describe reality accurately, the rules of quantum mechanics and the rules of relativity had to operate together. The theory that eventually emerged from this effort is known as quantum field theory. Quantum field theory combines the probabilistic behavior of quantum mechanics with the space-time structure described by special relativity. It provides a mathematical framework for understanding how particles can appear, disappear, and interact while still respecting the speed limits imposed by relativity. The basic idea is both simple and astonishing. Instead of treating particles as fundamental objects, quantum field theory treats fields as the true underlying ingredients of nature. Every type of particle corresponds to a specific field that fills the entire universe. These fields exist everywhere, even in the emptiest regions of space. When one of these fields vibrates in a particular way, the vibration appears as a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Quarks, neutrinos, and many other particles correspond to their own fields as well. In this view, particles are not independent objects moving through empty space. They are localized excitations of fields that already exist everywhere. To understand this idea, imagine a large, perfectly stretched drumhead. If the drumhead is completely still, nothing appears to be happening. But if you tap the surface lightly, a vibration travels outward across the material. The vibration is not separate from the drumhead. It is simply a pattern of motion within the drumhead itself. Quantum field theory suggests that particles behave in much the same way. They are not separate entities floating through the universe. They are patterns of vibration occurring within fields that fill space and time. Developing the mathematics behind this idea required the work of several brilliant physicists during the 1940s. Among them was an American physicist named Richard Feynman, who worked at institutions including Cornell University and later the California Institute of Technology. Feynman had a remarkable ability to visualize complex physical processes in simple, intuitive ways. One of his most famous contributions was the introduction of a graphical method for representing particle interactions. These diagrams, now known as Feynman diagrams, allow physicists to visualize how particles exchange energy and influence one another. In a typical diagram, lines represent particles traveling through space-time. Points where lines meet represent interactions between particles. For example, when two electrons repel each other through the electromagnetic force, they do so by exchanging a photon. In a Feynman diagram, this interaction appears as two electron lines connected by a photon line. The diagram is not merely a picture, it corresponds directly to mathematical expressions used to calculate the probability of the interaction occurring. Feynman diagrams became an extraordinarily powerful tool for performing calculations in quantum field theory. At roughly the same time, another physicist named Julian Schwinger was developing a different mathematical approach to the same problem. Schwinger worked primarily at Harvard University and focused on precise operator methods for calculating particle interactions. Meanwhile, a Japanese physicist named Shinichiro Tominaga was independently working on similar ideas, while based at the University of Tokyo. Tominaga's work was especially impressive because he carried out much of it during the difficult years of the Second World War, often with limited access to international scientific publications. Despite using different methods, the work of Feynman, Schwinger, and Tominaga ultimately described the same physical processes. All three physicists were studying how electrons and photons interact within the framework of quantum electrodynamics. Quantum electrodynamics, often abbreviated as QED, is the quantum field theory describing the electromagnetic interaction. QED became one of the most precise and successful scientific theories ever developed. For example, it can predict the magnetic properties of the electron with astonishing accuracy. Measurements of this property, known as the electron's magnetic moment, agree with theoretical predictions to more than 10 decimal places. This level of precision is sometimes compared to measuring the distance between two cities thousands of kilometers apart, and being accurate to within the width of a human hair. Eventually, the work of Feynman, Schwinger, and Tominaga was unified by another physicist named Freeman Dyson. Dyson demonstrated that the seemingly different approaches developed by these researchers were mathematically equivalent. In other words, they were different ways of expressing the same underlying theory. By showing how these methods fit together, Dyson helped clarify the structure of quantum electrodynamics and solidified the foundations of quantum field theory. With this framework in place, physicists began applying similar ideas to other types of particles and forces. The concept that each particle corresponds to its own field became central to the theory. The electron field exists everywhere in the universe. When this field vibrates in a particular way, we observe an electron. The electromagnetic field produces photons when it oscillates. Other fields correspond to particles such as quarks and neutrinos. Each field obeys its own set of equations describing how it evolves through spacetime. When two fields interact, their vibrations can influence one another. These interactions are what we observe as forces between particles. For example, the electromagnetic force arises when charged particles interact through the electromagnetic field. An electron generates a disturbance in the electromagnetic field. That disturbance travels outward and influences other charged particles nearby. In quantum field theory, this influence is described as the exchange of photons between charged particles. Although this may sound abstract, it produces very real and measurable effects. The repulsion between two electrons, the attraction between an electron and a proton in a hydrogen atom, and the transmission of light across enormous distances in space, all arise from the behavior of the electromagnetic field. The same principle extends to other forces as well. Different fields correspond to different interactions. These ideas transformed the way physicists think about the nature of reality. Instead of imagining particles as the fundamental building blocks of matter, quantum field theory places fields at the center of the picture. Particles become temporary excitations in these fields. They can appear, interact, and disappear, while the underlying fields remain present everywhere. Even empty space, often called the vacuum, is not truly empty. The fields that produce particles still exist in the vacuum. They can fluctuate, producing brief disturbances that sometimes appear as particle pairs before disappearing again. The universe, in this sense, is filled with a vast collection of fields quietly stretching across all of spacetime. Their vibrations create the particles we observe. Their interactions generate the forces of nature. And together they form the deep framework that modern physics uses to describe the structure of the cosmos. What once looked like a universe made from tiny solid particles now appears to be something far more subtle. A universe made from fields. Once physicists began thinking of the universe as a collection of quantum fields, a natural question followed. If fields truly are the fundamental ingredients of reality, then what fields actually make up the matter around us? The answer turns out to be both elegant and surprisingly economical. Every object you have ever touched, every rock, every drop of water, every living cell, and every star in the sky is built from just a handful of fundamental particles, and each of those particles arises from its own underlying field. The most familiar of these is the electron. The electron field fills the entire universe. It exists everywhere, from the interior of stars to the emptiest regions of intergalactic space. When the electron field vibrates in a particular way, that vibration appears as an electron. Electrons are extremely light compared with most other particles. Their mass is roughly 9/10 of a trillionth of a gram. To put that into perspective, it would take about 600 billion electrons to equal the mass of a single grain of sand. Despite their small mass, electrons play an enormous role in the structure of matter. They form the outer regions of atoms, interacting with atomic nuclei through the electromagnetic force. The patterns formed by electrons surrounding nuclei determine the chemical properties of elements. Chemistry itself is largely the story of how electrons arrange themselves around atoms and how those arrangements change during chemical reactions. But electrons are not the only matter particles. Deep inside the nucleus of every atom are protons and neutrons. These particles are much heavier than the electrons and contain almost all of the mass of ordinary matter. For many years, physicists assumed that protons and neutrons were fundamental particles, but in the 1960s, evidence began accumulating that they had an internal structure. Experiments at the Stanford Linear Accelerator Center in California played a key role in revealing this structure. Scientists fired high-energy electrons into protons and observed how the electrons scattered. The scattering patterns suggested that protons contained smaller components. Around the same time, theoretical work by Murray Gell-Mann at the California Institute of Technology and George Zweig at CERN independently proposed a bold new idea. They suggested that protons and neutrons were made of even smaller particles called quarks. Gell-Mann chose the unusual name quark after encountering the word in James Joyce's novel Finnegan's Wake. As a piece of trivia, physicists often joke that quarks may be the only particles whose name was borrowed from experimental literature. According to the quark model, protons and neutrons are not fundamental objects. Instead, they are combinations of smaller particles bound together by a powerful force. A proton contains 3 quarks, specifically 2 up quarks and 1 down quark. A neutron also contains 3 quarks, but arranged slightly differently. It contains 1 up quark and 2 down quarks. These quarks are held together by a force known as the strong nuclear force, which is carried by particles called gluons. Gluons themselves arise from another quantum field, known as the gluon field. The strong force is remarkably powerful. At the scale of quarks inside a proton, it is roughly 100 times stronger than the electromagnetic force that governs interactions between electrons. This force binds quarks together so tightly that isolated quarks have never been observed directly in experiments. Instead, quarks are always confined inside larger particles such as protons and neutrons. Together, quarks and electrons form the basic ingredients of ordinary matter. There is one more type of matter particle worth mentioning, though it interacts far more weakly with the rest of the universe. This particle is called the neutrino. Neutrinos are extremely light and carry no electric charge. They interact only through the weak nuclear force and gravity. Because of this, they pass through matter almost completely undisturbed. Every second, trillions of neutrinos pass through your body without leaving any noticeable trace. Most of them originate from nuclear reactions inside the Sun. Physicists first proposed the existence of the neutrino in 1930, when Wolfgang Pauli suggested that an invisible particle might be carrying away missing energy in radioactive beta decay. The neutrino was finally detected experimentally in 1956 by Clyde Cowan and Frederick Rains at the Savannah River Nuclear Reactor in the United States. Like electrons and quarks, neutrinos correspond to their own quantum fields. These fields extend throughout the universe, quietly producing particles whenever the conditions are right. When you combine all of these ingredients, a clear picture of matter begins to emerge. Quarks combine to form protons and neutrons. Protons and neutrons form the nuclei of atoms. Electrons surround those nuclei, forming structured clouds governed by quantum mechanics. The resulting atoms join together through electromagnetic interactions to create molecules. Molecules assemble into larger structures such as crystals, liquids, biological cells, and living organisms. But beneath all of these layers, the deeper reality remains the same. Every one of these particles corresponds to a vibration in a quantum field. The electron field produces electrons. The quark fields produce quarks. The neutrino fields produce neutrinos. Each field fills the universe continuously. The particles we observe are simply localized excitations within those fields. A useful comparison is again the surface of a lake. Imagine that the entire surface of the lake represents a field. When the surface is calm, nothing appears to be happening. But if ripples appear in certain regions, those ripples travel across the surface. Now imagine that different kinds of ripples exist on different invisible surfaces, layered across the same lake. One surface produces electron ripples, another produces quark ripples, another produces neutrino ripples. The real universe is not quite so simple, but the analogy captures the essence of the idea. Matter is not built from tiny solid objects moving through empty space. Instead, matter consists of stable patterns of vibration within multiple interacting fields. When these vibrations settle into stable arrangements, they produce the particles and atoms that make up the physical world. The atoms in your body, the oxygen you breathe, the silicon in computer chips, and the iron in the core of the Earth all arise from the same small set of quantum fields interacting in intricate ways. In this sense, everything around us is made from patterns within a deeper structure that fills all of space. Even the most solid objects, such as a granite rock or a steel beam, are ultimately arrangements of vibrating fields organized into stable configurations. Once this idea sinks in, the everyday world begins to look a little different. The solidity of matter becomes an emergent property of deeper physical processes. Objects become patterns, particles become vibrations, and the universe itself begins to resemble a vast and interconnected tapestry of quantum fields, quietly weaving the fabric of reality. When physicists began exploring quantum fields in greater detail, they noticed something remarkable. The laws governing these fields seemed to possess a deep kind of order. Beneath the complicated mathematics and unfamiliar concepts, there appeared to be a guiding principle shaping how the forces of nature behaved. That principle is symmetry. In everyday language, symmetry usually refers to balance or visual harmony. A butterfly has symmetrical wings. A snowflake displays symmetrical patterns. A perfectly round sphere looks the same from every direction. But in physics, symmetry has a more precise meaning. A symmetry exists when a system can undergo a transformation while leaving the underlying laws unchanged. For example, imagine performing an experiment in a laboratory today and then repeating the same experiment tomorrow. If the laws of physics remain the same from one day to the next, the universe possesses symmetry in time. Similarly, if you perform an experiment facing north and then repeat it facing east, the outcome will not change simply because the apparatus was rotated. This reflects a symmetry in space. These kinds of symmetries are not just aesthetic properties. They are deeply connected to the structure of physical laws. In the early 20th century, the mathematician Emmy Noether demonstrated a profound relationship between symmetries and conservation laws. Noether showed that every continuous symmetry of a physical system corresponds to a conserved quantity. For instance, symmetry in time leads to conservation of energy. Because the laws of physics do not change over time, energy cannot simply appear or disappear. Similarly, symmetry in spatial position leads to conservation of momentum. These insights revealed that symmetry is not merely decorative. It is a fundamental organizing principle of nature. As physicists developed quantum field theory, they began discovering new types of symmetry that were even more subtle. One particularly important form is known as gauge symmetry. Gauge symmetry governs how certain fields can be transformed without changing the observable physics of a system. Although the mathematical details can be complex, the central idea is surprisingly elegant. Imagine that you and a friend are each measuring temperature in different units. You might measure in degrees Celsius while your friend uses degrees Fahrenheit. The numerical values differ, but the underlying physical temperature is the same. Gauge symmetry reflects a similar freedom in how certain physical quantities can be described. The concept was first explored in the early 20th century by a German mathematician and physicist named Hermann Weyl. In 1918, Weyl proposed a theory in which certain physical quantities could be transformed locally without affecting the underlying laws of nature. Although his initial model did not fully match experimental observations, The idea introduced an entirely new way of thinking about symmetry. Weyl's concept of gauge invariance eventually became central to modern particle physics. Gauge invariance means that the equations describing a field remain valid even when certain mathematical transformations are applied at every point in spacetime. This requirement might sound abstract, but it has powerful consequences. In quantum field theory, demanding gauge symmetry actually determines how particles must interact with one another. In other words, the existence of certain forces arises directly from symmetry principles. One of the most important developments in this direction came in the year 1954. Two physicists, Chen-Ning Yang and Robert Mills, introduced a new type of gauge theory that extended Weyl's ideas. Yang and Mills proposed a framework in which fields possessed internal symmetries related to mathematical structures called non-abelian groups. Although that phrase may sound intimidating, the essential insight is simple. Yang and Mills showed that if a system obeys certain symmetry transformations, new fields must exist in order to preserve that symmetry. These new fields act as carriers of forces. The theory predicted the existence of particles that mediate interactions between other particles. These mediating particles are now known as gauge bosons. Gauge bosons include particles such as photons, which carry the electromagnetic force. Later developments extended the Yang-Mills framework to describe additional forces in nature, including the strong nuclear force and the weak nuclear force. In modern particle physics, the Standard Model is built almost entirely around gauge symmetry. Different forces correspond to different types of gauge symmetries. For example, the electromagnetic force arises from a symmetry known as the unitary one-gauge symmetry. The strong nuclear force, which binds quarks inside protons and neutrons, arises from a more complex symmetry called the special unitary three symmetry. These names refer to mathematical structures describing how fields can transform while leaving physical predictions unchanged. Although the terminology may sound technical, the underlying principle remains clear. Nature appears to organize itself according to patterns of symmetry. The forces between particles are not arbitrary. They arise because the underlying fields obey specific symmetry rules. If those symmetry rules were different, the forces of nature would be different as well. Atoms might not hold together. Stars might not shine. Chemistry might not exist. Symmetry acts as a kind of blueprint guiding how the fundamental fields of the universe interact. Another remarkable feature of gauge symmetry is that it helps ensure the consistency of physical laws across the entire universe. Whether an experiment is performed on Earth, on the Moon, or in a distant galaxy billions of light-years away, the same symmetry principles apply. The equations describing quantum fields remain valid everywhere. This universality gives physics its predictive power. Scientists can perform experiments in laboratories on Earth and use the results to understand processes occurring in the cores of stars or in the earliest moments of the universe. The reliability of physical laws is not an accident. It arises from the deep symmetries embedded in the structure of the universe. There is also something aesthetically appealing about this idea. Many physicists have noted that the most successful theories in science often display remarkable mathematical elegance. Symmetry plays a central role in that elegance. When the laws of nature can be expressed through symmetrical patterns, the resulting theories often turn out to be both powerful and predictive. Theoretical physicist Paul Dirac once remarked that it is more important for equations to be beautiful than to fit existing data perfectly. While experimental verification remains the ultimate test, history has shown that mathematical beauty often points toward deeper truths. In quantum field theory, symmetry is not simply a decorative feature added to the equations. It is the language that the equations themselves speak. Gauge symmetry tells us which fields must exist. It determines how those fields interact. It governs the behavior of the forces that shape matter and energy throughout the universe. Without symmetry, the entire framework of modern particle physics would collapse. With it, the behavior of quantum fields becomes both structured and understandable. The universe, it seems, follows patterns, and those patterns are written in the language of symmetry. As physicists explored the behavior of quantum fields during the 20th century, a remarkable pattern began to emerge. The growing collection of discoveries did not form a chaotic assortment of particles and forces. Instead, the evidence pointed toward a surprisingly organized structure. Over several decades, researchers gradually assembled a framework that now stands as one of the most successful scientific theories ever developed. This framework is known as the Standard Model of particle physics. The Standard Model is essentially a map of the fundamental quantum fields that appear to make up the known universe. It describes which fields exist, what particles arise from those fields, and how those particles interact with one another. At its heart, the model organizes particles into two broad categories. The first category consists of matter particles. These are the particles that combine to form atoms and all the structures we observe in the physical world. The second category consists of force-carrying particles. These particles arise from fields that transmit the fundamental forces of nature. Together, these components form an elegant system of interacting quantum fields. Let us begin with the matter particles. The Standard Model describes a group known as fermions. Fermions are particles that obey the Pauli exclusion principle, which means no two identical fermions can occupy the same quantum state simultaneously. This rule is essential for the stability of matter. Fermions are divided into two families called quarks and leptons. Quarks are the particles that combine to form protons and neutrons inside atomic nuclei. There are 6 known types of quarks, often referred to as flavors. Their names are up, down, charm, strange, top and bottom. The up quark and the down quark are the most common in ordinary matter. Protons contain 2 up quarks and 1 down quark, while neutrons contain 1 up quark and 2 down quarks. The other 4 quark types appear primarily in high-energy particle interactions and are rarely found in stable matter. The second group of fermions is the leptons. The most familiar lepton is the electron, which surrounds atomic nuclei and plays a central role in chemistry and electricity. The Standard Model also includes 2 heavier relatives of the electron called the muon and the tau particle. These heavier leptons behave similarly to electrons but decay rapidly into lighter particles. Each of these charged leptons is accompanied by a corresponding neutrino. Neutrinos are extraordinarily light and interact only weakly with other particles. Because they rarely interact with matter, enormous numbers of neutrinos pass through the Earth every second without leaving any noticeable trace. Physicists often remark that neutrinos are the universe's most elusive travelers. Together, the 6 quarks and 6 leptons form the basic matter particles of the Standard Model. But matter alone does not tell the whole story. Particles interact with one another through forces, and these forces are transmitted by another category of particles known as gauge bosons. Gauge bosons arise from the fields associated with the fundamental forces. The electromagnetic force is carried by photons. Photons arise from oscillations of the electromagnetic field and are responsible for phenomena ranging from visible light to radio waves and X-rays. The strong nuclear force which binds quarks together inside protons and neutrons is carried by particles called gluons. There are 8 varieties of gluons, and they arise from the gluon field associated with the strong interaction. The weak nuclear force, responsible for processes such as radioactive decay and nuclear fusion inside stars, is carried by 3 particles known as the W+ boson, the W- boson, and the Z boson. These particles are extremely massive compared with other force carriers, which explains why the weak force operates only over very short distances inside atomic nuclei. Together, these gauge bosons transmit the interactions that govern the behavior of matter particles. One of the most elegant aspects of the Standard Model is that these forces emerge from the symmetry principles described earlier. The theory describing electromagnetic interactions is known as quantum electrodynamics. The theory describing the strong force is called quantum chromodynamics, often abbreviated as QCD. Both of these theories are examples of gauge theories, meaning they are built upon symmetry principles that determine how the corresponding fields interact. Another remarkable development in particle physics occurred when scientists realized that 2 of the fundamental forces could actually be unified. During the 1960s, 3 physicists named Sheldon Glashow, Abdus Salam, and Steven Weinberg developed a theory showing that the electromagnetic force and the weak nuclear force are actually different aspects of a single unified interaction. This theory became known as the electroweak theory. According to electroweak theory, the electromagnetic and weak forces were once unified in the extremely hot conditions of the early universe. As the universe cooled, the symmetry connecting them broke, and the 2 forces began behaving differently. The concept that allowed this transformation to occur was introduced earlier by a Japanese physicist named Yoichiro Nambu. Nambu proposed the idea of spontaneous symmetry breaking. To visualize this concept, imagine placing a perfectly balanced pencil upright on its tip. In theory, the pencil could fall in any direction. The system begins in a perfectly symmetrical state, but once the pencil falls, the symmetry is broken. The laws governing the pencil remain symmetrical, but the actual outcome chooses a specific direction. In quantum field theory, spontaneous symmetry breaking occurs when the underlying equations remain symmetrical, but the lowest energy state of the system does not preserve that symmetry. This mechanism allows particles to acquire different properties, even though the fundamental laws remain symmetrical. The electroweak theory predicted the existence of the W and Z bosons long before they were observed experimentally. Confirmation arrived in the early 1980s at CERN, the European Organization for Nuclear Research located near Geneva, on the border between Switzerland and France. Physicists Carlo Rubbia and Simon van der Meer led experiments using the superproton synchrotron that successfully detected the W and Z bosons in 1983. Their discovery provided powerful confirmation that the electroweak theory was correct. Other components of the Standard Model were confirmed through experiments conducted at laboratories around the world. At Fermilab near Chicago, the top quark was finally discovered in 1995 after decades of searching. At CERN's Large Electron Positron Collider and later at the Large Hadron Collider, physicists tested numerous predictions of the Standard Model with extraordinary precision. Each successful experiment strengthened confidence in the framework. Today, the Standard Model stands as a detailed map of the known quantum fields that make up matter and transmit the forces of nature. It explains an enormous range of physical phenomena, from the interactions inside atomic nuclei to the behavior of particles produced in high-energy accelerators. Despite its success, the Standard Model is not believed to be the final theory of everything. It does not fully incorporate gravity, and it leaves several cosmic mysteries unresolved. But as a description of the known quantum fields and their interactions, it remains one of the most accurate and experimentally verified frameworks ever constructed in science. It reveals a universe that is far more structured and interconnected than early physicists could have imagined. Beneath the diversity of particles and forces lies a carefully organized system of fields interacting through the guiding principles of symmetry. And within that system, the familiar matter around us emerges as a stable arrangement of quantum fields quietly interacting throughout the vast expanse of space. One of the most curious questions in modern physics sounds deceptively simple. Why do particles have mass? At first glance, mass seems like a basic property of matter. A rock has mass, a planet has mass, even the smallest particles appear to possess mass. But when physicists began constructing the mathematical framework of quantum field theory, they encountered a surprising difficulty. The equations describing the fundamental forces worked best when many particles were treated as if they had no mass at all. In particular, the elegant symmetry principles underlying the electroweak theory required certain particles to behave as though they were massless. Yet experiments clearly showed that many particles do possess mass. Electrons have mass. Quarks have mass. The W and Z bosons that carry the weak nuclear force are extremely massive compared with most other particles. The challenge was to understand how particles could acquire mass while still preserving the mathematical symmetries required by the theory. During the 1960s, several physicists independently proposed a solution that would eventually reshape our understanding of the universe. The key idea was that mass might not be an intrinsic property of particles at all. Instead, it could arise through interactions with an invisible field permeating all of space. Among the scientists who developed this concept were Peter Higgs at the University of Edinburgh, François Englert and Robert Brute working in Brussels, and another group consisting of Gerald Guralnick, Carl Hagen, and Tom Kibble. Although these researchers worked independently, they arrived at closely related conclusions. Their work described a mechanism in which a new quantum field fills the entire universe. When particles interact with this field, they experience resistance to acceleration, which manifests as mass. This idea became known as the Higgs mechanism. To understand the concept intuitively, physicists often use simple analogies. Imagine walking through a completely empty room. You can move freely and quickly without much resistance. Now imagine that the room is crowded with people. As you try to move across the room, you must push past others who slow your motion. In this analogy, the crowded room represents the Higgs field. Particles that interact strongly with the Higgs field experience greater resistance as they move. This resistance appears to us as mass. Particles that interact weakly with the field behave as if they are lighter. Some particles, such as photons, do not interact with the Higgs field at all. As a result, they remain massless and travel at the speed of light. The Higgs field therefore acts like a kind of invisible medium filling the entire universe. Its presence affects how different particles move through space-time. But this description raises an important question. If the Higgs field exists everywhere, why does it not disrupt the symmetry principles that govern the fundamental forces? The answer lies in a phenomenon known as spontaneous symmetry breaking. Earlier we discussed how symmetry plays a central role in modern physics. Many equations describing quantum fields possess symmetrical structures that treat different states equally. However, the lowest energy state of a system does not always preserve that symmetry. A useful analogy comes from a perfectly round hill with a ball balanced at its peak. The hill is symmetrical because every direction looks the same, but the ball cannot remain balanced forever. When it eventually rolls down, it must choose a particular direction. The symmetry of the hill remains, but the state of the system has chosen one outcome. In quantum field theory, the Higgs field behaves in a similar way. The equations describing the field are symmetrical, but the lowest energy state of the field corresponds to a non-zero value throughout space. Physicists describe this by saying that the Higgs field has a non-zero vacuum expectation value. In simpler terms, the field does not vanish in empty space. Instead, it maintains a constant background presence everywhere in the universe. Particles moving through this background interact with it, and those interactions produce the property we interpret as mass. This mechanism allowed the electroweak theory developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg to remain mathematically consistent, while still explaining the observed masses of particles. But there was still one more prediction. If the Higgs field truly existed, it should produce a new particle associated with vibrations of the field itself. This particle became known as the Higgs boson. For decades, the Higgs boson remained one of the most sought-after particles in physics. Detecting it required enormous experimental energies because the particle is extremely massive and short-lived. To search for it, physicists constructed increasingly powerful particle accelerators. The most ambitious of these machines is the Large Hadron Collider at CERN near Geneva. The Large Hadron Collider is a circular accelerator buried deep underground. It consists of a tunnel approximately 27 kilometers in circumference. Inside this tunnel, powerful superconducting magnets guide beams of protons traveling at speeds extremely close to the speed of light. When these proton beams collide, they release tremendous amounts of energy concentrated in a tiny region of space. According to Einstein's relationship between energy and mass, extremely energetic collisions can produce heavy particles that would not normally appear in low-energy environments. In spoken form, that relationship can be expressed clearly. Energy equals mass multiplied by the speed of light squared. Using this principle, high-energy collisions can briefly create particles such as the Higgs boson. On the 4th of July in the year 2012, physicists at CERN announced that two major experiments known as ATLAS and CMS had detected signals consistent with the long-predicted Higgs boson. The discovery confirmed a crucial piece of the Standard Model. It provided direct evidence that the Higgs field exists and that particles gain mass through interactions with it. The particle observed in these experiments had a mass of roughly 125 billion electron volts, making it more than 100 times heavier than a proton. Although the Higgs boson itself exists only for an extremely short time before decaying into other particles, its discovery demonstrated that the Higgs field is a real and measurable component of the universe. The importance of this field extends far beyond particle physics laboratories. Without the Higgs field, many particles would have no mass at all. Electrons would travel at the speed of light instead of forming stable orbitals around atomic nuclei. Protons and neutrons would behave very differently as well. Atoms would not form in the familiar way, and the complex chemistry that allows molecules and biological structures to exist would be impossible. In other words, the existence of stable matter depends critically on the presence of the Higgs field. It quietly fills the universe, shaping the masses of particles and enabling the formation of atoms, molecules, planets, and living organisms. Although we cannot see the Higgs field directly, its effects are woven into the structure of everything around us. Every solid object, every chemical reaction, and every biological process depends on the masses of particles that arise through this subtle interaction. What once seemed like a simple property of matter turns out to emerge from a deeper layer of the universe, an invisible field spread across all of space, quietly giving weight to the particles that build the world we experience. If we could somehow remove every atom, every photon, and every particle from a region of space, what would remain? For most of scientific history, the answer seemed straightforward. Nothing would remain. The region would simply be empty space. But modern quantum field theory paints a far more intriguing picture. Even the most perfect vacuum imaginable is not truly empty. In quantum physics, empty space is filled with quantum fields. These fields exist everywhere. Whether or not particles are present, they cannot be turned off or removed. What we call the vacuum is simply the lowest energy state of those fields. And even in this lowest energy state, the fields are not perfectly still. Instead, they constantly fluctuate. These tiny temporary disturbances are known as quantum fluctuations. To understand why fluctuations occur, we need to return briefly to one of the central ideas of quantum theory, the uncertainty principle, introduced by Werner Heisenberg. The uncertainty principle tells us that certain pairs of physical quantities cannot both be specified with perfect precision. One version of this principle relates energy and time. In spoken form, the relationship can be summarized as follows. The uncertainty in energy multiplied by the uncertainty in time must always be greater than or equal to Planck's constant divided by 4 times pi. This principle means that energy in a system cannot remain perfectly fixed over extremely short time intervals. For brief moments, small amounts of energy can appear and disappear, as long as they do so within the limits allowed by the uncertainty principle. In the context of quantum fields, this leads to an astonishing consequence. Even in empty space, fields can briefly produce small excitations before returning to their lowest energy state. These fleeting disturbances can behave like tiny particles that appear and vanish almost instantly. Physicists often refer to these short-lived excitations as virtual particles. The term virtual particle can be slightly misleading because these entities are not particles in the usual sense. They cannot be detected directly as individual objects. Instead, they are mathematical representations of temporary fluctuations in quantum fields that contribute to interactions between real particles. Richard Feynman's diagram method provides a useful way to visualize these processes. In a Feynman diagram, lines represent particles moving through space-time, while interaction points show how particles influence one another. Virtual particles often appear in these diagrams as intermediate lines connecting other particles. For example, when 2 electrons repel each other through the electromagnetic force, the interaction can be described as the exchange of a virtual photon. The photon appears briefly as a disturbance in the electromagnetic field before disappearing again. Although these virtual particles cannot be observed directly, their effects are measurable. They influence how particles scatter in experiments, how forces behave at extremely small distances, and how energy shifts occur in atomic systems. One of the most famous demonstrations of vacuum fluctuations was predicted in the 1940s by the Dutch physicist Hendrik Casimir. Casimir studied the behavior of quantum fields between 2 closely spaced metal plates. According to classical physics, if 2 metal plates were placed extremely close together in empty space, nothing special should happen. But quantum field theory predicts a subtle effect. Between the plates, certain wavelengths of the electromagnetic field cannot exist because the metal surfaces restrict the possible patterns of vibration. Outside the plates, however, the field can fluctuate freely across a wider range of wavelengths. This difference in allowed fluctuations produces a small imbalance in pressure. As a result, the plates experience a tiny attractive force pulling them toward each other. This phenomenon became known as the Casimir effect. The force involved is extremely small, but it has been measured experimentally with high precision in laboratories. For example, when 2 plates are separated by a distance of about 100 nanometers, which is roughly 1,000th the thickness of a human hair, the Casimir force becomes detectable using sensitive instruments. The observation of this effect provided compelling evidence that quantum fluctuations are not merely theoretical ideas. They have real physical consequences. The vacuum, it seems, is not empty at all. It is a restless background filled with fluctuating fields. Even when no particles are present, the underlying quantum fields continue to vibrate and interact. Another striking consequence of vacuum fluctuations appears in the behavior of atomic energy levels. In the late 1940s, physicists Willis Lamb and Robert Rutherford measured a tiny shift in the energy levels of hydrogen atoms. This phenomenon, now known as the Lamb shift, occurs because the electron in a hydrogen atom interacts with fluctuations of the electromagnetic field surrounding it. The quantum vacuum subtly alters the energy levels of the atom. Such effects reveal that even the quietest regions of space remain active at the smallest scales. The vacuum behaves less like empty nothingness and more like a complex sea of invisible activity. Quantum fields are constantly fluctuating, producing brief disturbances that influence particles and forces. This dynamic nature of the vacuum has important implications for our understanding of the universe. For example, some physicists suspect that vacuum energy may play a role in cosmic phenomena such as dark energy, which appears to be driving the accelerated expansion of the universe. The precise relationship between quantum vacuum energy and cosmology remains one of the great open questions in modern physics. What is clear, however, is that the classical idea of empty space has been completely replaced. Space is not an inert stage on which physical events unfold. Instead, it is filled with quantum fields that are always present and always active. Even when the universe appears quiet and still, those fields continue their subtle fluctuations beneath the surface. Invisible ripples constantly appear and vanish. Particles briefly flicker into existence before dissolving back into the vacuum. And the fabric of space-time itself remains alive with microscopic activity. In the language of quantum field theory, the vacuum is not the absence of everything. It is the lowest energy state of a universe filled with fields, a state that may look empty from afar but up close is anything but quiet. To understand how quantum fields influence the universe today, it helps to imagine what the universe looked like at the very beginning. The earliest moments of cosmic history were unimaginably different from the calm and spacious universe we experience now. Temperatures were extraordinarily high, densities were extreme, and energy filled every region of space. In those early fractions of a second, the familiar particles and structures of matter had not yet formed. Instead, the universe consisted almost entirely of interacting quantum fields and their energetic fluctuations. Modern cosmology describes this period through the framework known as the Big Bang Theory. According to this model, the observable universe began approximately 13.8 billion years ago in a state of tremendous density and temperature. As the universe expanded, it gradually cooled, allowing particles, atoms, stars, and galaxies to form over vast stretches of time. Yet the earlier stages of this expansion present a number of puzzles. For example, distant regions of the universe appear to have nearly identical temperatures, even though they are separated by distances so large that light could not have travelled between them since the beginning of cosmic expansion. This observation suggests that these regions were once in close contact before being carried far apart. Another puzzle concerns the geometry of the universe. Measurements show that the large-scale structure of the universe is remarkably flat, meaning that the curvature of space-time is extremely close to zero. Without a special mechanism, maintaining such flatness throughout cosmic history would require extremely precise initial conditions. In the late 1970s and early 1980s, physicists proposed a bold idea to explain these mysteries. The idea became known as cosmic inflation. Cosmic inflation describes a period of extremely rapid expansion that occurred during the earliest moments of the universe. During this brief interval, space itself expanded exponentially, growing by an enormous factor in a tiny fraction of a second. One of the first scientists to develop this concept was Alan Guth, a theoretical physicist working at the Massachusetts Institute of Technology. In 1980, Guth proposed that the early universe may have undergone a phase transition involving a quantum field that temporarily trapped the universe in a high-energy state. This field acted somewhat like a compressed spring storing energy. When the universe was in this state, the energy density remained nearly constant even as space expanded. Because the energy density did not decrease, the expansion accelerated dramatically. Within an incredibly short time, regions of space that were once microscopic could grow to astronomical size. Although inflation lasted only a tiny fraction of a second, it would have increased the size of the universe by a factor of at least 1 followed by 30 zeros. That number is sometimes described as a factor of 10 raised to the power of 30. Such enormous expansion would explain why distant regions of the universe now appear so similar. Before inflation occurred, those regions were close enough to exchange energy and reach a uniform temperature. Inflation then stretched them far apart. The concept of inflation also helps explain the observed flatness of the universe. Rapid expansion tends to smooth out curvature, much like inflating a balloon makes its surface appear flatter over larger regions. Although Alan Guth introduced the original inflationary idea, later physicists refined the theory in important ways. One of the earliest models of inflation had already been proposed by the Soviet physicist Alexei Starobinsky in the late 1970s. Starobinsky's model used modifications of Einstein's theory of gravity to produce rapid expansion in the early universe. Later still, physicist Andrei Linde developed additional versions of inflation that solved certain technical problems in Guth's original proposal. Linde's models, sometimes called chaotic inflation, suggested that inflation could arise under a wider range of conditions than originally expected. Despite their differences, these models shared a central idea. A quantum field in the early universe drove a brief period of explosive expansion. This field is often referred to as the inflaton field. Although the exact identity of the inflaton field remains uncertain, its behavior can be described using the language of quantum field theory. As the inflaton field slowly changed over time, its energy density powered the expansion of space. Eventually the field decayed into ordinary particles, releasing enormous amounts of energy and filling the universe with radiation. This process marked the transition from the inflationary era to the hot, dense universe described by the traditional Big Bang model. But inflation did more than simply expand the universe. It also amplified tiny quantum fluctuations present in the inflaton field. Earlier we discussed how quantum fields cannot remain perfectly still. Even in their lowest energy states, they exhibit small fluctuations caused by the uncertainty principle. During inflation, these microscopic fluctuations were stretched by the expanding universe. Disturbances that began at subatomic scales grew to cosmic proportions. Over time, these tiny variations in density became the seeds of the large-scale structures we observe today. Regions that were slightly denser attracted more matter through gravity. Other regions became slightly emptier. Over billions of years, these differences grew into the vast cosmic web of galaxies and clusters that fill the observable universe. In this way, the large-scale structure of the cosmos may trace its origins back to tiny quantum fluctuations in fields during the earliest moments of time. Evidence supporting this picture comes from careful observations of the cosmic microwave background. The cosmic microwave background is faint radiation that fills the universe in every direction. It represents the afterglow of the early universe approximately 380,000 years after the Big Bang, when atoms first formed and light was able to travel freely through space. This radiation carries a snapshot of the universe at that time. Measurements of the cosmic microwave background reveal extremely small temperature variations across the sky. These variations correspond to tiny differences in density present in the early universe. Several major scientific missions have mapped these fluctuations with remarkable precision. The Wilkinson Microwave Anisotropy Probe, often abbreviated as WMAP, operated from 2001 through 2010 and produced detailed measurements of the cosmic microwave background. Later, the European Space Agency launched the Planck satellite, which operated between 2009 and 2013. Planck provided the most precise map of the cosmic microwave background ever created. The patterns observed in these maps match the predictions made by inflationary models. The tiny temperature variations correspond to density fluctuations that originated from quantum fluctuations during inflation. These observations suggest that the enormous structures of galaxies and clusters we see today ultimately grew from microscopic fluctuations in quantum fields. In other words, the distribution of galaxies across the universe may have begun as tiny ripples in quantum fields during the earliest moments of cosmic history. This idea reveals something profound about the relationship between quantum physics and cosmology. The smallest scales of nature and the largest structures in the universe are connected. Quantum fields operating at subatomic distances helped shape the formation of galaxies spanning hundreds of thousands of light years. The quiet fluctuations of fields in the early universe left imprints that still echo across the cosmos today, and in that sense the galaxies we see scattered across the night sky may trace their origins back to subtle vibrations in the quantum fields that filled the universe at the dawn of time. For all the success of the standard model of particle physics, the universe still holds some deeply puzzling mysteries. One of the most significant involves a strange form of matter that we cannot see directly. Astronomers call it dark matter. The name does not mean the substance is literally dark in the sense of being black or shadowy. Instead, it means that this matter does not emit, absorb, or reflect light in any detectable way. Yet despite being invisible, its presence can be inferred through its gravitational influence. The first strong clues appeared during the 1970s through the work of an astronomer named Vera Rubin. Rubin was studying the motion of stars within spiral galaxies. In particular, she measured how quickly stars were orbiting the centers of those galaxies. According to Newtonian gravity, the speed of stars should depend on how much mass lies inside their orbits. In the outer regions of a galaxy, where most of the visible matter has already been passed, stars should orbit more slowly. The expected pattern resembles the motion of planets in our solar system. Mercury moves quickly around the Sun, while distant planets such as Neptune travel much more slowly. But Rubin's observations told a very different story. Using spectroscopic measurements at the Carnegie Institution for Science and the Kitt Peak National Observatory, Rubin and her collaborator Kent Ford discovered that stars in the outer regions of galaxies were moving far faster than expected. Instead of slowing down with distance from the galactic center, their orbital speeds remained nearly constant. This result implied that galaxies contained far more mass than could be accounted for by visible stars, gas, and dust. Something else was present, something that exerted gravitational influence, but did not emit light. Subsequent observations confirmed Rubin's findings in many galaxies. Further evidence for dark matter appeared through studies of galaxy clusters, gravitational lensing, and the large-scale distribution of galaxies across the universe. Gravitational lensing occurs when massive objects bend the path of light from distant sources, an effect predicted by Albert Einstein's theory of general relativity. Measurements of gravitational lensing often reveal much stronger gravitational fields than can be explained by visible matter alone. Together, these observations suggest that most of the matter in the universe is invisible. Current estimates indicate that ordinary matter, composed of protons, neutrons, and electrons, makes up only about 5% of the total energy content of the universe. Dark matter appears to account for roughly 27%. The remaining portion is attributed to an even more mysterious component known as dark energy. The crucial question is this: what exactly is dark matter made of? One possibility is that dark matter consists of particles arising from quantum fields that have not yet been discovered. These fields would exist alongside the familiar fields described by the Standard Model, but interact extremely weakly with ordinary matter. Over the years, physicists have proposed several candidates for these hypothetical particles. One of the earliest ideas involves a particle known as the axion. The axion was originally proposed in the 1970s by Roberta Pechet and Helen Quinn. Their work addressed a subtle problem in the theory of quantum chromodynamics, which describes the strong nuclear force binding quarks inside protons and neutrons. Quantum chromodynamics allows certain mathematical terms that would produce a violation of a symmetry known as charge parity symmetry. However, experiments showed that this violation does not occur in the strong interaction. Pechet and Quinn proposed a mechanism that naturally eliminates the unwanted effect by introducing a new field. This field gives rise to a particle called the axion. Although the axion was initially introduced to solve a theoretical problem, physicists later realized that axions could also be excellent candidates for dark matter. Axions would be extremely light and interact very weakly with ordinary particles, making them difficult to detect. Yet enormous numbers of axions could fill the universe, forming a background field that contributes to the total mass of galaxies. Another major class of dark matter candidates is known as weakly interacting massive particles. These particles are often abbreviated as WIMPs. WIMPs are predicted in several extensions of the Standard Model, including theories involving supersymmetry. The basic idea is that WIMPs would have masses comparable to heavy atomic nuclei, but interact only through the weak nuclear force and gravity. Because their interactions are so weak, WIMPs could pass through ordinary matter almost unnoticed. Even so, if enough of them exist in the galaxy, a tiny fraction might occasionally collide with atoms in extremely sensitive detectors. To search for these rare events, physicists have constructed elaborate underground experiments designed to shield detectors from cosmic rays and other sources of background noise. Among the most advanced of these experiments is Xenon-NT, located deep beneath the Gran Sasso mountain in Italy. This detector uses a large tank filled with liquid xenon. If a dark matter particle collides with a xenon atom, it can produce a tiny flash of light and a faint electrical signal. sensitive instruments record these signals in hopes of identifying the signature of a dark matter interaction. Another major experiment is LUX-ZEPLIN, often called LZ, located nearly 1 mile underground at the Sanford Underground Research Facility in South Dakota. Like Xenon-T, the LZ experiment also uses liquid xenon to search for extremely rare particle collisions. A third program known as Supercryogenic Dark Matter Search, abbreviated as SuperCDMS, operates detectors cooled to extremely low temperatures. These detectors measure tiny vibrations produced when particles interact with specialized crystals. Despite decades of searching, no confirmed detection of dark matter particles has yet been achieved. However, each experiment improves the sensitivity of the search, narrowing the range of possible properties that dark matter particles could possess. If dark matter particles are eventually discovered, they would almost certainly correspond to new quantum fields beyond those included in the standard model. Such a discovery would dramatically expand our understanding of the fundamental structure of the universe. It would reveal that the collection of known fields is incomplete, and that additional fields remain hidden within the fabric of reality. This possibility is one of the reasons physicists continue to search for dark matter with such determination. The stakes are enormous. If dark matter consists of previously unknown fields, then the universe may be far richer than our current theories suggest. Invisible fields could be quietly permeating space, shaping the motion of galaxies and influencing the evolution of cosmic structure. Just as earlier discoveries revealed electrons, quarks, and neutrinos as excitations of quantum fields, dark matter may represent another layer of fields that have so far remained hidden from direct observation. And if that turns out to be true, the familiar map of known particles and forces will need to be redrawn. The standard model would become only one chapter in a much larger story about the quantum fields that fill the universe. Among the 4 known forces of nature, gravity occupies a rather unusual position. The electromagnetic force, the strong nuclear force, and the weak nuclear force are all described successfully by quantum field theory. Their behavior emerges from interactions between quantum fields and the particles associated with those fields. Gravity, however, is described by an entirely different framework. The modern theory of gravity was developed by Albert Einstein in the early 20th century and is known as general relativity. Instead of describing gravity as a force transmitted between particles, general relativity explains gravity as the curvature of space-time itself. According to Einstein's theory, massive objects such as stars and planets distort the geometry of space-time around them. Other objects moving through that curved geometry follow paths determined by the shape of space-time. A useful mental image is to imagine placing a heavy ball on a stretched rubber sheet. The sheet bends under the weight of the ball. Smaller objects rolling across the sheet move along curved paths because the surface itself is curved. In general relativity, space-time replaces the rubber sheet, and massive objects warp the geometry around them. The relationship between matter and space-time curvature can be summarized in a compact statement often attributed to physicist John Archibald Wheeler. Matter tells space-time how to curve, and space-time tells matter how to move. Einstein's theory has been tested in numerous ways over the past century. It correctly predicts the bending of light around massive objects, a phenomenon known as gravitational lensing. It explains the slight shift in the orbit of the planet Mercury that could not be accounted for by Newtonian gravity. More recently, observations by the Laser Interferometer Gravitational Wave Observatory, commonly called LIGO, have detected gravitational waves produced by collisions between black holes and neutron stars. These waves are ripples in spacetime itself, traveling outward across the universe at the speed of light. Despite its extraordinary success, general relativity is not a quantum theory. It treats spacetime as a smooth, continuous structure rather than a fluctuating quantum field. This difference creates a deep conceptual challenge. Quantum field theory describes the behavior of particles and forces at extremely small scales, often much smaller than atoms. General relativity describes gravity at much larger scales, such as stars, galaxies, and the expanding universe. When physicists attempt to apply both theories simultaneously in extreme environments, such as the center of a black hole, or the earliest moments of the Big Bang, the mathematical descriptions become incompatible. In quantum field theory, fields fluctuate and particles appear and disappear according to probabilistic rules. In general relativity, spacetime itself is treated as a continuous geometric structure that does not fluctuate in the same quantum sense. Trying to quantize gravity in the same way as other forces leads to mathematical infinities that cannot easily be removed. This problem has challenged physicists for decades. One of the approaches developed to address this difficulty is known as loop quantum gravity. Loop quantum gravity is a theoretical framework that attempts to describe gravity using quantum principles without introducing additional particles or dimensions. This approach was developed in part by physicists Carlo Rovelli and Lee Smolin during the 1980s and 1990s. Their work builds upon earlier ideas introduced by physicist Abhay Ashtekar. Ashtekar discovered a new mathematical formulation of Einstein's equations that allowed gravity to be expressed in a way more compatible with quantum theory. Using these new variables, researchers found that spacetime itself might possess a discrete structure at extremely small scales. In loop quantum gravity, spacetime is not perfectly smooth. Instead, it may be composed of tiny units or loops that form a network sometimes called a spin network. These loops represent quantized units of geometry. Distances and areas in this framework cannot take arbitrary values. Instead, they come in discrete amounts, much like energy levels in quantum mechanics. If this picture is correct, the familiar smooth fabric of spacetime would emerge from an underlying network of quantized structures. The scale at which these quantum geometric effects become important is incredibly small. Physicists often refer to the Planck length, which is roughly 1.6 times 10 to the negative 35 meters. To appreciate how small this is, consider that a proton has a diameter of about 1.6 times 10 to the negative 15 meters. The Planck length is therefore about 20 orders of magnitude smaller than the size of a proton. At such scales, the smooth geometry described by general relativity may break down and reveal a more fundamental quantum structure. Loop quantum gravity attempts to describe how this underlying structure behaves and how the familiar geometry of spacetime emerges from it. Other approaches to quantum gravity exist as well, including string theory, which proposes that particles arise from vibrating strings existing in higher dimensional spaces. Despite decades of effort, a complete and experimentally verified theory of quantum gravity has not yet been achieved. Part of the difficulty lies in the enormous energies required to probe physics at the Planck scale. The energies needed to directly observe quantum gravitational effects are far beyond the capabilities of current particle accelerators. As a result, researchers must rely on indirect clues from cosmology, black hole physics, and mathematical consistency. The challenge of unifying gravity with quantum field theory remains one of the greatest unsolved problems in physics. If such a unification is achieved, it would bring together the two most successful frameworks in modern science. Quantum field theory would describe the behavior of particles and fields. General relativity would describe the geometry of spacetime. A complete theory would reveal how these two aspects of reality emerge from a deeper and more unified structure. It would explain how spacetime itself behaves at the smallest scales and how quantum fields interact with the geometry of the universe. In many ways, this search represents the next step in the long journey that began when physicists first realized that particles might actually be vibrations in invisible fields. The ultimate goal is to understand not only the fields that fill spacetime, but spacetime itself. And somewhere within that deeper structure may lie the next great insight into the nature of the universe. Even with the enormous success of quantum field theory and the Standard Model, many physicists suspect that the story may not end with fields alone. The Standard Model describes an impressive collection of quantum fields that generate the particles and forces we observe. Yet it leaves several deep questions unanswered. Gravity still stands apart from the quantum framework, dark matter remains mysterious, and the mathematical structure of the Standard Model appears incomplete in certain subtle ways. Because of these open questions, some researchers have explored the possibility that quantum fields themselves might not be the most fundamental ingredients of reality. Instead, they might emerge from something even deeper. One of the most ambitious attempts to uncover that deeper structure is known as string theory. String theory proposes that the basic building blocks of nature are not point-like particles at all. Instead, the fundamental entities are tiny vibrating strings. These strings are extraordinarily small. Their length is believed to be close to the Planck scale, roughly 1.6 times 10 to the negative 35 meters. To appreciate how tiny that is, imagine shrinking a proton down to the size of the observable universe. Even at that scale, a fundamental string would still be far too small to see. In string theory, each string can vibrate in different patterns. These patterns correspond to different particles, One vibration might behave like an electron, another vibration might behave like a photon. Yet another pattern could correspond to a quark. In other words, particles emerge as different vibrational states of a single fundamental object. This idea carries a certain elegance. Rather than requiring a separate field for each type of particle, the universe could arise from a single underlying structure whose vibrations produce the diverse particles we observe. The origins of string theory trace back to the late 1960s. At that time, physicists were attempting to understand the strong nuclear force that binds quarks together inside protons and neutrons. An Italian physicist named Gabriele Veneziano discovered a mathematical formula that accurately described certain patterns seen in particle scattering experiments. Although Veneziano initially viewed the formula as a useful mathematical tool, other physicists soon realized that it could be interpreted as describing vibrating strings. Among the early pioneers exploring this interpretation was Leonard Susskind, who later became a prominent figure in theoretical physics. Susskind and others began developing the idea that particles might arise from tiny strings rather than point-like objects. Over the following decades, string theory expanded into a complex and far-reaching framework. One of the physicists who played a major role in advancing the theory was Edward Witten at the Institute for Advanced Study in Princeton. Witten's work helped unify several versions of string theory and revealed deep mathematical connections between them. In the mid-1990s, Witten proposed that the various string theories might actually represent different aspects of a single overarching theory often referred to as M-theory. Although the full details of M-theory remain uncertain, the idea suggested that the underlying structure of the universe could be richer and more intricate than previously imagined. One of the most surprising features of string theory is the requirement for additional spatial dimensions. The familiar universe appears to contain 3 dimensions of space and 1 dimension of time, but the mathematics of string theory works consistently only if additional dimensions exist. Most versions of the theory require a total of 10 spacetime dimensions, while certain formulations of M-theory involve 11. These extra dimensions are not thought to extend across large distances like the familiar dimensions of space. Instead, they may be compactified into extremely small shapes, curled up so tightly that they remain invisible at ordinary scales. To visualize this concept, imagine a long garden hose lying on the ground. From a distance, the hose appears one-dimensional. You can move along its length, but its circular cross-section is too small to notice. However, if you examine the hose closely, you discover that it has an additional circular dimension around its circumference. In a similar way, the extra dimensions predicted by string theory may exist at scales far smaller than anything we can currently observe. Another intriguing element of string theory involves objects known as branes. The term brane comes from the word membrane and refers to higher dimensional surfaces that can exist within the framework of the theory. In some models, our entire observable universe may be confined to a 3-dimensional brane embedded within a higher dimensional space. Particles corresponding to the standard model would be restricted to this brane, while gravity might propagate through the larger multi-dimensional space surrounding it. These ideas sound exotic, but they arise naturally from the mathematical structure of string theory. The theory attempts to provide a unified description of all forces, including gravity, within a single consistent framework. One particularly attractive feature of string theory is that it automatically includes a particle that behaves like the graviton. The graviton is the hypothetical quantum particle associated with the gravitational field. When physicists analyze the vibrations of strings, one of the vibrational modes naturally possesses the properties expected for a graviton. This suggests that gravity might emerge naturally within the theory. If string theory is correct, quantum field theory itself might represent only an approximation of a deeper reality. At low energies and large distances, the vibrations of strings could appear as quantum fields and particles. In this way, the familiar framework of quantum field theory would arise as an effective description of the behavior of strings at scales accessible to current experiments. The situation would be somewhat similar to the relationship between water waves and molecules. When we watch waves moving across the surface of the ocean, we often describe them in terms of smooth patterns and flowing motion. But at a deeper level, the water consists of enormous numbers of individual molecules interacting with one another. The wave description works well at large scales, even though the underlying reality is composed of discrete particles. String theory suggests that quantum fields might play a similar role. Fields would describe the large-scale behavior of deeper structures built from vibrating strings. Although string theory has produced many fascinating insights and mathematical connections, it remains difficult to test experimentally. The energy scales required to probe strings directly are far beyond the capabilities of current particle accelerators. As a result, string theory remains a theoretical framework rather than a confirmed physical theory. Even so, its ideas have influenced many areas of physics and mathematics, from black hole thermodynamics to quantum information theory. The possibility that quantum fields themselves might emerge from an even deeper layer of vibrating strings reminds us that our understanding of the universe is still evolving. What appears fundamental today may one day be revealed as a manifestation of something more basic. And somewhere within those deeper structures may lie the next great step toward understanding the invisible architecture of the cosmos. As physicists continued exploring the deep structure of quantum fields, gravity, and space-time, an idea began to emerge that sounded almost philosophical at first. What if the universe we experience is not the most fundamental layer of reality? What if the three-dimensional world around us is actually a kind of projection arising from deeper information encoded elsewhere? This possibility is captured in a concept known as the holographic principle. The holographic principle was first proposed during the 1990s by two theoretical physicists, Gerard 't Hooft and Leonard Susskind. Their idea was inspired by an unexpected puzzle involving black holes. Black holes are regions of spacetime where gravity becomes so strong that nothing, not even light, can escape once it crosses the boundary known as the event horizon. In the 1970s, physicist Stephen Hawking discovered that black holes are not completely black after all. Due to quantum effects near the event horizon, black holes emit a faint form of radiation now known as Hawking radiation. This discovery raised an intriguing question. If a black hole slowly evaporates through Hawking radiation, what happens to the information about the matter that originally fell into it? In classical physics, information about a system is never destroyed. Yet Hawking's calculation suggested that black holes might erase information entirely. This possibility became known as the black hole information paradox. In trying to resolve this paradox, physicists noticed something surprising about the entropy of black holes. Entropy is a measure of the amount of information or disorder in a physical system. Normally, the entropy of a system grows with its volume. However, the entropy of a black hole appears to scale with the surface area of its event horizon, rather than the volume inside it. The formula describing black hole entropy was developed by Jacob Bekenstein and Stephen Hawking. In spoken form, the relationship can be summarized clearly. The entropy of a black hole equals 1/4 of the surface area of its event horizon divided by the Planck length squared. The crucial point is that the entropy depends on the area of the surface, not the volume of the interior. This observation led 't Hooft and Susskind to propose a radical idea. Perhaps the fundamental information describing a region of space is encoded on its boundary surface rather than throughout its volume. In other words, the three-dimensional world we experience might emerge from information stored on a two-dimensional boundary. The analogy often used is that of a hologram. A hologram is a two-dimensional surface that stores information about a three-dimensional image. When light interacts with the surface in the right way, a fully three-dimensional image appears. The holographic principle suggests that the universe might behave in a somewhat similar manner. The physics inside a region of space could be encoded on a lower dimensional boundary surrounding it. While this idea initially sounded almost speculative, it gained strong support from a remarkable discovery in the late 1990s. In 1997, physicist Juan Maldacena proposed a mathematical relationship known as the anti-de Sitter and conformal field theory correspondence, often abbreviated as ADS-CFT correspondence. Maldacena's insight revealed that certain theories of gravity in a curved spacetime can be exactly equivalent to quantum field theories defined on the boundary of that spacetime. In other words, a gravitational universe existing in a higher dimensional space could be mathematically identical to a quantum field theory living on a lower dimensional surface. This duality provided the first concrete example of the holographic principle operating within a consistent theoretical framework. Although the specific version studied by Maldacena involves an idealized space-time geometry called anti-de Sitter space, the deeper lesson was profound. Gravity and space-time geometry might emerge from underlying quantum systems without gravity. The holographic correspondence has since become one of the most powerful tools in theoretical physics. Researchers use it to study strongly interacting quantum systems, black hole physics, and even aspects of condensed matter physics. Perhaps even more intriguing is the possibility that space-time itself might be an emergent phenomenon. In everyday experience, space and time appear to form the basic stage on which physical events occur, but holographic theories suggest that space-time geometry might arise from deeper relationships between quantum states. One area of research exploring this idea involves quantum entanglement. Quantum entanglement occurs when two or more particles become linked in such a way that measuring one instantly influences the state of the other, even if they are separated by great distances. Although entanglement has been confirmed experimentally many times, its deeper implications are still being explored. Physicist Mark van Raamsdonk has proposed that spacetime geometry may actually emerge from patterns of quantum entanglement between underlying degrees of freedom. In this picture, the fabric of spacetime is not fundamental. Instead, it arises from the way quantum systems are connected through entanglement. When quantum systems become strongly entangled, they form a coherent structure that behaves like continuous spacetime. If the entanglement were removed, spacetime itself might fragment or disappear. This idea suggests that geometry and gravity could emerge from the information structure of quantum fields. In other words, spacetime might be built from relationships between quantum states rather than existing as an independent entity. The implications of this perspective are remarkable. It suggests that the universe may operate more like a vast information processing system than a traditional collection of particles moving through empty space. Quantum fields, entanglement, and information may form the deeper layer from which spacetime and gravity arise. Some physicists even speculate that the entire observable universe might behave like a holographic projection of deeper physical processes. The familiar three-dimensional world would then represent a kind of emergent description of information encoded in more fundamental degrees of freedom. Although these ideas remain areas of active research, they illustrate how dramatically our understanding of reality has evolved. The journey began with the discovery that matter dissolves into atoms, atoms dissolved into particles, particles dissolved into quantum fields, and now even fields and spacetime themselves may emerge from deeper structures involving information and entanglement. If the holographic principle turns out to describe nature accurately, it would mean that the universe we experience is not the ultimate layer of reality. Instead, it could be the visible surface of something far deeper, a projection of hidden quantum processes unfolding beyond the limits of our current understanding. Throughout the history of physics, a familiar pattern appears again and again. Each time scientists believe they have reached the deepest layer of reality, new discoveries reveal that something even more fundamental lies beneath. Atoms were once thought to be indivisible building blocks of matter. Later they were found to contain electrons, protons, and neutrons. Protons and neutrons were then revealed to contain quarks. Particles themselves turned out to be excitations of quantum fields, and now even those fields may not represent the final layer of nature's structure. Many physicists suspect that the theories we use today may describe only an effective level of reality, much like the way the laws of fluid motion describe water without referring directly to individual molecules. At larger scales, the behavior of water can be captured by equations describing pressure and flow. But at deeper levels, those properties arise from the interactions of vast numbers of molecules. Similarly, quantum field theory may represent a highly accurate description of phenomena at accessible energies, while still emerging from deeper structures that have yet to be fully understood. In recent years, several theoretical ideas have begun exploring what that deeper structure might look like. One particularly intriguing development involves a geometric object known as the amplituhedron. The amplituhedron was introduced in the year 2013 by theoretical physicist Nima Arkani-Hamed and his collaborators Jaroslav Trnka and others, working at the Institute for Advanced Study in Princeton. The amplituhedron emerged from attempts to simplify the extremely complicated calculations required to describe particle interactions. In quantum field theory, predicting the outcome of particle collisions often involves enormous mathematical expressions built from Feynman diagrams. As the number of interacting particles increases, these calculations become extraordinarily complex. Arkani-Hamed and his collaborators discovered that certain scattering amplitudes, which describe the probability of particles interacting in specific ways, could be calculated using a geometric structure rather than traditional equations. This structure is the amplituhedron. Instead of summing vast numbers of Feynman diagrams, The amplituhedron encodes the same information within a higher dimensional geometric object. The volume of this object corresponds directly to the probability amplitudes governing particle interactions. What makes the amplituhedron particularly fascinating is that the usual ingredients of physics appear to disappear within this framework. Traditional concepts such as space-time coordinates and local interactions do not explicitly appear in the calculations, yet the results match those obtained through standard quantum field theory. This suggests that space-time and locality, two concepts normally treated as fundamental, might actually emerge from deeper mathematical relationships. The amplituhedron hints that the true structure underlying particle interactions could be purely geometric. If this idea proves correct, it would mean that the familiar language of fields and particles might eventually be replaced by a more fundamental description based on geometry and information. Another line of research exploring deeper mathematical structures comes from twistor theory. Twistor theory was pioneered by Roger Penrose during the late 1960s. Penrose proposed that the fundamental description of reality might be better expressed in terms of mathematical objects called twistors, rather than points in spacetime. In twistor theory, spacetime is not the primary arena of physics. Instead, the fundamental objects exist in a different type of mathematical space, where geometric relationships capture the behavior of particles and fields. Within this framework, certain calculations that appear complicated in ordinary spacetime become simpler and more elegant. Twistor methods have proven particularly useful in studying scattering amplitudes and have influenced the development of modern amplitude-based approaches in quantum field theory. Although twistor theory has not yet replaced conventional descriptions of spacetime, it continues to inspire new ways of thinking about the structure of physical laws. Both the amplituhedron and twistor theory point toward a similar possibility. The fundamental structure of the universe might not consist of particles moving through space-time. Instead, space-time itself might arise from deeper mathematical relationships. This idea connects with other developments in theoretical physics. Research into quantum information, entanglement, and holography increasingly suggests that the fabric of space-time could emerge from patterns of information shared among quantum systems. In such pictures, geometry is not a starting point but an outcome. Distances, curvature, and gravitational effects might emerge from the way quantum states are organized and connected. This perspective is still being explored, and many details remain uncertain. Yet the direction of research suggests that physics may be approaching another conceptual shift. Just as atoms dissolved into particles, and particles dissolved into fields, fields themselves may one day dissolve into something even more fundamental. Perhaps the ultimate description of nature will involve networks of information. Perhaps geometry will arise from abstract mathematical relationships. Or perhaps an entirely new principle will emerge that reshapes our understanding once again. For now, quantum field theory remains one of the most successful frameworks ever developed in science. It explains the behavior of particles and forces with extraordinary precision, and has been confirmed repeatedly through experiments conducted in laboratories around the world. Yet the questions that remain are profound. What truly lies beneath the fields? Why does the universe possess the particular symmetries and structures we observe? How do spacetime, gravity, and quantum mechanics ultimately fit together? The search for answers continues in research institutes, universities, and particle physics laboratories across the globe. Scientists explore new mathematical frameworks, analyze data from powerful detectors, and develop increasingly sophisticated theories. Each discovery reveals a little more about the invisible architecture of reality, and each new insight reminds us that the universe may be far deeper than our current understanding suggests. What we call fundamental today may eventually turn out to be only the surface of a far richer structure. The quantum fields that fill the universe may themselves be ripples within something even more profound, and in that sense, the journey toward understanding the deepest layer of reality may still be only beginning.